ladies and gentlemen. Our next speaker is Professor Duan from Tsinghua University, and the title of his talk is Faster Matrix Multiplication via Asymmetric Hashing. And this is the FSA award in the SABS. So let's warmly welcome Professor Duan.
Okay, so we'll consider matrix multiplication. Okay, so this is the that's the definition of the matrix multiplication. And want to find the time complexity. How many operations do we need to compute C? Okay, so the time bound is the time complexity of the matrix multiplication is usually denoted by the n to the omega plus small o1. So we care about the number of omega. So we know that omega is less than 3 because trivially, if we compute by definition, is n cubed time, right? Because every element we need n operations, n cubed time. But because output is n squared elements, so the best we can do is n squared. So omega is at least 2. So we know that omega is a constant between 2 and 3. We don't know what is the exact value of the omega right now. So Strenson's 2 times 2 algorithm give the first algorithm better than n cubed time. That is, if we want to compute the multiplication of this 2 times 2 matrix, and Strenson algorithm trivially it needs 8 multiplications, right? But Strenson algorithm have 7 multiplications. So we can do a divide and conquer approach. We only need 7 multiplications. So divide and conquer approach is and running time n to the log 7 base 2, so equal to this, n to the 2.8074, like that. So this is the first algorithm with n cubed time. And this is a current time bound. Okay. So the best so far is like 2.7371, like that. Okay. And this paper is this bound. So first we'll see that is the time complexity n to the omega is related to many other problems. So these are some problems which can be accelerated by the fast matrix multiplication algorithms, like the linear operations, or some other matrix multiplication, or other graph theory algorithms. For example, the LUP decomposition, it's just a Gauss elimination. That is, want to make the matrix to be the multiplication of lower triangle matrix and upper triangle matrix and the permutation matrix. So, in fact, it's just Gauss elimination. That is, we want to make the element here and here, so they are all 0. So make it an upper triangle matrix. Because after the LP decomposition, so for example, compute determinant and solving linear system or finding inversions, that becomes easy. And also find inverse of a triangle matrix. Find the inverse of a triangle matrix takes n to the omega time. Right? Because here, if this is a upper triangle matrix, so inverse equal to this. So one need to recursively compute the upper triangle matrix of A and B, and needs matrix multiplication. So it had time n to the omega, the same as matrix multiplication. Okay. So then we can accelerate the LUP decomposition, accelerate the Gaussian elimination. Because trivially, Gaussian elimination is like we erase those elements. And so this is a Hopcroft bunch algorithm. So you limit elements like this. Every time we can compute the inverse of a triangle matrix. For example, to eliminate this matrix, we need to compute the inverse of this one. But this one is already an upper triangle matrix. So this means that Gaussian elimination can be done into the omega time. So this means that these three operations have the same time complexity into omega, right? Because matrix inversion can be reduced to LUP decomposition, and LUP decomposition can be reduced to matrix multiplication. And matrix multiplication can also be reduced to matrix inversion because of this. If I compute matrix inversion, we can compute A times B. So many such matrix operations has the same time complexity by matrix multiplication. So it can be accelerated by fast matrix multiplication algorithms. And also, linear programming now also has learning time like this. Okay. So current bound, we know that current bound is like 2.3714, so on. And alpha, current bound of alpha is 0.3213. So when omega equal to 2, alpha equal to 1. So of course, maybe this algorithm is so optimal. Still not optimal. Then first define what is alpha. So alpha is that it's based on rectangular matrix multiplication. For example, time complexity for multiplying n to the A times n to the B matrix, and n to the B times n to the C matrix. It is denoted by this. So exponent is denoted by omega ABC. Then alpha is largely constant such that 1 alpha 1 equal to 2. Meaning that we multiply this n to the n times n to the alpha, and this n to the alpha times n. So the output is n times n matrix. So once that time complexity is nearly the same as the size of the output. So alpha is at the largest such alpha, satisfying this. The current bound is like this. Also, there are also other parameters. For example, the mu. Mu is the number satisfying this omega 1 mu 1 equal to 1 plus 2 mu. Current bound is like 0.5 5275. This. So many other. This is also useful in many algorithms. For example, the maximum weakness. That is in metric multiplication, Boolean metric multiplication, defined as this. So Cij equal to 1 if there's the case so that Aik and Bkj are both 1. But the maximum weakness means that if Cij equal to 1, we want to find the maximal k for each ij, for such ij, such that Aik equal to Bkj equal to 1. And we want to find a maximum a weakness which is the Grace-Moss weakness. So of course, this algorithm can be accelerated by rectangular measurement multiplication because we can just compute, divide it into maybe n to the k parts, n over n to the k parts. So every matrix is n times n to the. So we can compute n over n to the k rectangular measurement multiplication of this. Then by this method, we can find which part the maximum weighting is in for every element. Then we can check it one by one. That is, we'll first locate which part contains the maximum weightings. And then we enumerate elements inside it one by one. If you compute the time complexity, it will be like this. Balance these two is equal to this. So time complexity of this algorithm is like n to the 2 plus mu. Right. And also matching can also be accelerated by metric multiplication. So here, profile matching is that a matching is a set of vertex disjoint edges. And profile matching means that there's no free vertex. That every vertex is matched. But we can decide whether graph contains a profile matching by computing determinant. Because this is a definition of determinant. So if this is a adjacent matrix of a bipartite graph, then we can see determinant is the sum of this. This is a permutation. And permutation means that every row and column contain exactly one element. So it's just corresponding to a so that is if this is a bipartite graph, and contrast is adjacent matrix. So if there's no edge, it's 0. If there's an edge, there's a variable. So a profile matching corresponds to a non-zero term in the determinant. So from the definition of determinant, so determinant will be a polynomial of these variables. Which means that if there's no profile matching, then determinant is identically 0. So this determinant is a polynomial. So we can use polynomial identity testing. That is, we can assign each variable a random value, and compute its determinant. And we know that the computing determinant takes into omega time. So we can also repeat to reduce error probability. So by computing determinant, we can also check whether it's solving the matching problem. And right now, there is a maximum weight matching in general graph. O times W times n to omega time in graph with integer edge weights. But still, there's no like n to omega times log n time, log W time. What do you mean? So we have an algorithm like m times square root of n times log n W. So there's still no such edges. So there's still no such algorithm using measure multiplication to reduce log W. And also, opera shorty paths. Let's say given a graph, we want to find the distance between every two verses. So let's watch our Dasher algorithm for all verses takes n cubed time. But we don't know how to let's use measure multiplication to accelerate it. Okay, for the general case, let's do for the real weighted graph, opera shorty path. So there's still no truly subcubic time algorithm for opera shorty path for real weighted graphs. And for the opera shorty path, it's related metric operation. It's called mean path product. That you can define this. Originally, this is multiplication. This is path. But here we replace this by path, and this operation by minimal. So this mean path product have the same complexity as the opera shorty path. We know that. But right now, there's still no for the original multiplication, we have better algorithms than in cube. But for the mean path product, for the general case, for the real weighted case, there's no truly subcubic time algorithm. But for the unweighted case, for example, for the undirected unweighted opera shorty path, it now has n to the omega time algorithm. And for directed unweighted opera shorty path, we have n to the 2 path mu algorithm like this. So now the algorithm has the same time bound as maximum weightness, n to the 2 path mu. And if we want 1 path epsilon approximate opera shorty path, like n to the omega times log W over epsilon. So for such cases, it can be accelerated by measure multiplication. Also, the bottom line part means that I think this is because strengthening algorithm needs the inverse of this operation, the sum. If you look at it, it needs the inverse operation of this sum, but there's no inverse for minimal. So it looks like computing minimal is easier than computing sum or multiplication, but then we cannot use strengthening divide and conquer approach. The bottom line part is that we want to find a path with maximal flow from S to T. That's the one path with maximal flow, and so the flow depends on the minimal capacity on that path. So we want to maximize it. So the bottom line part is also called widest path. So the metric operation related to it is a mean path product. So mean path product is that it's the minimum of AIK and BKJ. I want to maximize it. So we know that this algorithm original metric multiplication has n to omega. Mean path product. But the max mean product now that have algorithm like n to the 3 plus omega over 2. The middle point between omega and 3. So this will be 2.6857 like that. It's also using the fast metric multiplication algorithm to accelerate. Also, there's other problems. For example, the bounded difference mean path product. Bounded difference means that adjacent entries only differ by a constant. The matrix, so every two adjacent elements only differ by a constant. The mean path product, if you consider the mean path product of two bounded different matrices, it can be accelerated by fast metric multiplication to break n cube time. Also, for the more general case, we can consider the mean path product of monotone matrices. So it's a more general case, and now we have an algorithm also reach this bound 3 plus omega over 2. So this monotone matrices and bounded different matrices has lots of applications. I have proved that all of such problems can be accelerated by this problem, the mean path product of monotone matrices. So we can see this algorithm now has running time like this into omega. And this problem has running time like 2 plus mu. And all of those have now has 2 plus omega over 2. So if omega equal to 2, then 2 plus mu and this 2 plus omega over 2 are both 2 point n to the 2.5. So this problem has the running time like this, but we don't know whether they are equivalent. They can reduce each other. Okay, let's look at now. Let's look at the metric multiplication algorithm. Let's go back to the strengthened algorithm. So that's another way to in fact, it's another way to write the strengthened algorithm. Consider this tensor. This is ijk from 1 to 2, aik times bkj times cji. Then can be written like this. And each mi is a multiplication of two linear combinations of a and b, elements n, a and b. So which means that each of these terms is a multiplication of linear combination of a and b and c. So this means that strengthened algorithm can be represented as this. So this tensor can be written as the sum of 7 products, where each product is a linear combination of the entries of matrix A, B, C respectively. So we call such tensor the metric multiplication tensor, and divided this by 2 to 2. So this means that this tensor equal to, that is the sum of 7 such products. So this one is the metric multiplication tensor. So similarly, we can denote this one. Let's say I from 1 to n and j from 1 to n, k from 1 to p by n and p, a and p tensor. So the minimum m for such representation. That is, if this tensor can be represented by the sum of m such products. So the minimum of such m is called the rank of t, denoted by RT. So strengthened algorithm means that R of this tensor 2 to 2 is less equal to 7. So omega is less equal to log 7 base 2. And generally, omega is, we can have a bound like log n R, this tensor n. So in fact, this just that's another representation of the divide and conquer approach. So we know that if the tensor of the symmetric, if they are triples of n, it can be like this. But what about the general case n, m, and p? They are different. But this tensor is symmetric, right? That the ABC can be changed arbitrarily. So it's symmetric among A, B, and C. So the rank also equal. R A and P equal to R M and P equal to R P M N and so on. Also, the tensor product of these two. N1 M1 P1, N2 M2 P2 equal to this. Okay, and their rank can also be, if this one less equal to R1 and this one less equal to R2, then the rank of the tensor product is less equal to R1 times R2. You can just think of it as a divide and conquer step. That is, first we divide the matrix using this, and then divide the matrix using this. Then we can see that this NMP, the triple of NMP, is less equal to R NMP cube. In fact, that is, if I have the rank for such NMP tensor, we can also compute the square matrix multiplication. And now the formula like this, omega less equal to log NMP of this time, this rank, let's go to 3 times log NP R. So we can also, if we use tau to represent this, then tau is a bound on omega. Let's say omega less equal to 3 times tau. Also we can so this can also be written as RNP equal to NMP to the tau, where tau is a bound on omega, in fact, on omega over 3. So that's strengthen like the algorithm. So we know that we can compute 2 times 2 matrix multiplication in 7 multiplications. Right? So it can be accelerated. And then people try to find other methods, right? Other way to divide and conquer this method. So Victor Pan in 1979 showed that all of this 70 is less equal to this, which improves omega. Also have this bound. So in 2022, DeepMind used neural networks to find ranks of smaller tensors, and these are the results of DeepMind find. So if I compute it, so this one gives a better bound than this tensor. This is R4 triple 4 is less equal to 47. Then the bound becomes 2.778. But still, it's not the best bound for such strengthen-like algorithm. Because the original strengthen algorithm is 2 times 2 matrix is 7. So it's 4 times 4 matrix is 49. So it improves strengthen algorithm. But then people find other way to solve that. In 1979, they have a approach. They find a way to do that. So this is epsilon times this plus epsilon squared times this. And if we ignore the epsilon squared, we can see this one has 6 terms. So this will correspond to measurable coefficient of these two metrics. But this part is equal to 0. So have 6 terms. Then how to use that? We can merge 2 of these together. Because these are 5 modifications, which means that we can compute 3 times 2 times 2 tensor in 10 modifications. So omega becomes 3 times log 10 to the base of 12 equal to 2.78. But in fact, this is an exact algorithm, not an approximate algorithm. We can compute the matrix, the exact solution of the measurement modification. Okay. Because even with epsilon, the terms is bounded by n, in fact. So if we take the nth tensor power, this one will be negligible. So we can make omega. So this method, such method is also can compute the measurement coefficient exactly, not approximate. Even it seems that it has epsilon here. Then such representation is called the minimum m to do that. That is, there are m products here, but the result is that I have epsilon to dt and then plus some higher power of epsilon. Then such m is called the border rank of t. But such border rank can also compute a measurement modification. Can be used to compute measurement modification. Then people try to find other way to do that. That is to really improving the omega. Schulhager's approach. Schulhager discovered the following surprising identity. Then you can see it computes the measured product of 4 times 1 matrix and 1 times 4 matrix. So the result is a 4 times 4 matrix. And here, X is a 1 times 9 matrix, Y is a 9 times 1 matrix, and Z is 1 times 1. It's just one element. We can compute A times B and X times Y independently. So in the result, you can see ABC and S1Z are not related to each other. Right? So we can compute them independently in 17 multiplications. So in this case, we write like this: the border rank of tensor 414, and this is direct sum of the rank of 191. The border rank of this direct sum is less than or equal to 17. Direct sum means that the tensor are on distinct variables. emphasize that the two products concern independent matrices. So then Schoenhager's tau theorem means that how to find the bound for omega from that. We can just need to find the tau such that 17 equal to 16 to the tau plus 9 to the tau. And we compute it, we have omega less than equal to 2.5479, like that. So it's greatly improved from the strength algorithm. More generally, that is, if we can independently compute such metric multiplication tensors in m steps, we just need to find such the tau satisfying this, and we should give a bound on omega.这个实在太不可思议了。So this is Schoenhager's tau theorem. Okay. So now the current method is based on all based on the Copper-Smith Vinograd tensor, which is in 1990. And our approach is finding the combination loss and partially compensated for it. And note that there was a lower bound of 2 times 3725 in a paper maybe 10 years ago. But in fact, we changed the internal structure of the higher power tensor, so we can break such lower bound. It doesn't satisfy the condition of such lower bound. So first we will see the Copper-Smith Vinograd algorithm. So this is the tensor they find. And if we have making it blocks, that is x0 is one block, and s1 to sq is one block. And we use a superscript. So this denotes 0, and this denotes 1. So here there are q plus 2 products. And the things we get is like this. So what we can compute is that z is equal to this one. But they're not independent. So we cannot directly use it to find omega, because here these three terms are not independent, right? For example, the z1 appears in this term and also in this term, so that are not independent. But how to find the independent modification using such tensor? So let's take 3n tensor power of this. Then the left-hand side will be q plus 2 to the 3n multiplications. Right-hand side is a sum of these. Because for every term, the sum of the superscript or 2. So for all such if we look at the variable, for all such blocks, for every index, the sum of ijk equal to 2, then there's a term in this sum. For example, this will be another sum in the on the right hand side, because every index sums to 2. Which means that for every xi, yj, zk is in many terms. ijk are the blocks. Then the challenge is how to get independent maximum multiplication tensor. So because of time limits, we can. That is, we only we only keep the ijk such that they are exactly n levels and 2n ones. Which means that for every term, you can compute q to the n times q to the n metric products. So Copeland Van der Waals method means that it further level out such blocks until we get independent measurement multiplication. So they use a hashing method. They use the hashing method to do that. So after calculation, so the number of independent terms that is remaining is 3n choose n to the 1 minus epsilon prime. So the loss is very small, in fact. That is, we can guess this number of independent terms. By the Schoenhager-Tau theorem, we can compute this number of independent tensors, q to the n times q to the n tensors, with q plus 2 to the 3n multiplications. Then by Schoenhager-Tau theorem, okay. If we use this method to approximate the combinatorial. So have a bound like 2 points for there was 3. That is, we can choose q equal to 8. Okay, and then have this bound. Also, then further, Copeland Van der Waals add actual terms. For example, this q plus 1, and we have the superscript 2 on here. Then we have actual terms like 002. But you can see for every term here, the sum of the superscript is still 2. Originally, it's 011. We have a term, but here 002 can also have a term. Then using the previous method, Okay. Then we can see the combinatorial number becomes larger. We can design the block like this. Then the number block is this, and we compute it. We can reduce the omega to this 2.387. Then to improve this time bound, common Smith and Will grad also consider the second power of this tensor. Let's take a tensor square of it. Then analyze the second tensor power of CWQ. That is for every term where the super3 is 4, there's a term. Then by analyzing this one, we can see for tensor containing 0, it is itself a matrix multiplication tensor. So for the 0, 4, 0, 1, 3, and 0, 2, 2, they are matrix multiplication tensors. But for the 1, 1, 2, we still need a further hashing method to make it a matrix multiplication tensor. Let's see, by this method, so can make omega further to 2.3754, like that. That is by analyzing the second tensor power, it improves the omega a little bit. In fact, then people try to analyzing further tensor powers. For example, the fourth power, we make this bound, and eighth power. But you can see the amount of improvement becomes exponentially small. But in Coppersmith and Winograd paper, they explain why it can improve by taking higher tensor power. But in fact, if you analyze it in detail, you can see the improvement it's from the, because when using the higher tensor power, for the subtensor containing 0, we directly using it without hashing. Because originally we use a whole hashing, but here, for some part, we directly using it without hashing, meaning that it's merging. It's like merging. It's like originally it's hashing. We can get a squared numbers of tensors, b times t, b tensors. But after merging, italic. So the number of elements we use, if the same, then it will be AB times AB matrix. So by merging, we can computing more. Then our method is that we find that, in fact, higher tensor power can improve the omega a little bit. But if we look at in detail, we can see, in fact, the number of variables you use decrease, in fact. This is because if we look at the stability distribution of 2, for example, if you look at the stability distribution of 2 on Z, then in 202, the stability distribution lambda, this is lambda. In 112, look at the stability distribution mu. And they are different, in fact. Oh, that is, their lambda is almost twice of mu in CW's method, which means that if such combinatorics are different, meaning that the number of the combination, the number of variables we used is smaller than if we use the average stability distribution on the whole alpha, on the whole part. That is, if we choose using them as the same ratio, the number will be larger than if you're using different ratio. Then how to compensate this combination loss? So this means that the number of variables used in second power of Z-bar tensor is less than the first power. Although it's increased by merging, but the number of variables we use is becomes smaller. So how to compensate this? We use a asymmetric hatching method, so that is each Z is matched to multiple of X and Y. And we show that, in fact, each of these X, Y, and Z can compute almost independent matching multiplications. Okay. So this is our idea. But here we only reuse Z. X, Y are still not reused. So this only compensate for a small part of the combination loss. So there are many details. And the recent paper is that we use a method which is asymmetric in all of the X, Y, and Z. Get back the bound. Okay. So the idea is like that, but to find optimize the parameters is very complicated. So for this, we only get the bound for the fourth power. Okay, that's all.
Thank you for Professor Duan's presentation. Now, because of the time, we may ask some quick questions. you have any questions?
The usual objection, or as I understand it, for Strassen's algorithm and presumably some of the successors is that the matrices have to be very large for practical applications to actually for this to be useful. How does this compare in kind of, let's say, how large does n have to be before this takes over from a conventional?
Okay, so that's just a theoretical bound because you
I
can see.
understand that.
Okay. So because every part we assume epsilon equal to approach that one and approach infinity. You compare that bound. So it'll be very large.
Thank you for sharing. Introducing this new operation, do you think do you think there will be another lower bound like a 2014 paper? If there is, do you think it's greater than 2?
What do you mean?
You mentioned that only with hashing, there is a lower bound, right, on the power. 2014 stock paper, Evo Filmus et al.
But such lower bound is not, in fact, not only also depends on some condition, I think.
I see.
Okay, maybe not so solid, I think.
I see.
Any more questions? If there is no further questions, let's conclude this session. And thank you all for coming.